Just as with discrete random variables, there exist special or named continuous probability models. Perhaps the most commonly known is the normal or Gaussian model. For example, shown here are density plots of the observed wrist and bicep circumferences among a sample of 250 adults. At right, the normal probability models provide a reasonable representation of the behavior in these two biological variables among the broader population of adults. In fact, the normal model is so nicknamed because of how common or applicable it is in practice, beyond just wrists and biceps. This model has a more formal name, the Gaussian, named after an 18th century mathematician. Here we have these same two normal models, except plotted side by side in the same frame with the same y-axis scale. These highlight some important features of the normal probability density function, or PDF. First, as for any continuous random variable model, the normal PDF is scaled to have an area of 1. Second, normal PDFs are always symmetric and bell-shaped. Finally, the normal PDFs are defined by two parameters. Pause for a moment and ask yourself, what are two key differences between wrist and bicep circumferences? That is, what two parameters distinguish between these two random variables? Well, the centers of the PDFs differ. Wrist measurements vary around a typical measurement of 18 centimeters, whereas bicep measurements vary around 32 centimeters. We'll represent this parameter, the center of a normal model, by the Greek letter mu, as in mu like a cat. Further, the spreads of the PDFs differ. There's much more variability in biceps than in wrists from person to person. We'll represent this parameter, the spread of a normal model, by the Greek letter sigma. Though we won't get into the details yet, mu and sigma actually measure special properties of a normal model, its mean and standard deviation, respectively. We'll use these terms throughout the video, but won't define them more precisely until a future lesson. In general, let x be any normal random variable with mean mu and standard deviation sigma. This is represented by the notation here, which indicates the random variable of interest, here x, the assumed model that describes the randomness in x, here the normal model n, and the parameters that define this model, here mu and sigma. But this is just a label for the normal model. This model can be specified by a formula for its bell-shaped probability density function. Now don't worry about memorizing this formula. Let's just recognize some patterns. First, notice that the PDF depends upon the model parameters mu and sigma. Second, the curviness of the PDF is defined by an exponential function. And the quadratic term in this exponent ensures that the curve is symmetric around mu. Together then, these pieces ensure the bell shape of the normal PDF. Next, notice that the highlighted multiplier does not depend upon x, thus it serves as a normalizing constant. That is, it ensures the bell-shaped PDF has an area of 1. Dropping this normalizing constant, the normal PDF is proportional to its kernel. Finally, the support of the continuous normal PDF is the entire real line. That is, a normal random variable x can technically take on any value between negative and positive infinity. This support means that the normal model is almost always wrong in practice, but it can still be useful. For example, reconsider wrist circumferences. Unlike the formal normal model of wrists at right, actual human wrist circumferences cannot be negative or infinitely big. But the normal model still provides a reasonable representation of wrist circumferences. Though its PDF isn't technically 0 outside the reasonable range of wrists, it's effectively 0 outside that range. Finally, let's calculate some normal probabilities and use these to better understand the normal parameters mu and sigma. To this end, we'll focus on the random variable x, wrist circumference. X can be well represented by a normal model centered around a mean of 18 centimeters, mu, with a standard deviation sigma of 1 centimeter. The corresponding PDF with the formula here is plotted at left. Notice that the x-axis is marked in increments of 1 centimeter, the standard deviation of wrist circumferences. As indicated by the shaded area, our question is this: what's the probability that a person's wrist circumference is within 1 standard deviation of a mean? That is, between 17 and 19 centimeters. This probability can be calculated by integrating the PDF from 17 to 19. Given the more complicated PDF formula, this is tough to do by hand, but a computer can tell us that this probability is roughly 0.68. That is, roughly 68% of people have wrist circumferences between 17 and 19 centimeters. Thus, 32% total have circumferences outside this range, 16% falling below 17 centimeters and 16% falling above 19 centimeters. Let's consider a wider range. What's the probability that a person's wrist circumference is within 2 standard deviations of the mean? That is, between 16 and 20 centimeters. Roughly 95% of people have wrist circumferences in this range, with 5% total falling outside. Bumping it out one last time, roughly 99.7% of people, or almost everybody, has wrist circumferences that fall within 3 standard deviations of the mean, that is between 15 and 21 centimeters. What we've observed in our wrist calculations is referred to more generally as the 68, 95, 99.7 rule for the normal model. For any normal random variable x that's centered at mean mu with standard deviation sigma, there's a roughly 68% chance that x falls within 1 standard deviation from the mean mu, a roughly 95% chance that x falls within 2 standard deviations from the mean, and a roughly 99.7% chance that x falls within 3 standard deviations from the mean. Stepping back from the details, this rule helps us understand the connection between the sigma parameter and the spread of typical x values. It's also a handy way to quickly approximate normal probabilities without grabbing for a computer.